Welcome to homogeneous linear systems. So, quick definition, a linear first order system is said to be homogeneous if the forcing function is identically zero, so in other words, the forcing function is just identically the zero vector. Then the differential equation, or then the system takes the form y prime, again, this is the vector y prime, is equal to a of t, where a is the coefficient matrix, times the vector y, or the vector function y. Just a quick fact, just like we had for homogeneous differential equations, if y1 through yk are solutions to the homogeneous system, y prime equals a of ty, then any linear combination is also a solution. So any linear combination so anything y equals c1 y1 plus all the way through ck yk is also a solution. Again, we can just plug this in and see that it happens. You can distribute the multiplication by the matrix to each individual and pull out the scalars, and we are left with just zero. For another definition, just like we had for homogeneous differential equations, we once again will have a fundamental set of solutions. So y vector solution, or vector function y1 through vector function yn form a fundamental set of solutions to the system y prime equals a of t y, with n, which is an n by n system, right? In equations m unknown functions, if so y1 through yn form a fundamental set of solutions if every solution can be written in the form y equals c1 y1 plus all the way through cn yn. And we call this form the general solution. So far the language and the theory should look very similar to what we've seen before. It's just now we're working with vector functions, right, where we have a vector of n functions in each of our solutions. Quick definition, y1 through yn vector functions are said to be linearly independent if the linear combination C1, Y1 plus all the way through plus Cn, Yn equals 0 occurs if and only if C1 through Cn are all equal to 0. And otherwise, we would have some multiple ways to get 0, multiple ways to get the same solution, and they would be linearly dependent. Again, this should look familiar. It's the same as our linear algebra definitions. So we have a theorem which says solutions, oops, y1 through yn. So solutions y1 through yn to the equation y prime equals a of t times y. These form a fundamental set. Oh, I should specify again where this is an n by n system and equations in n unknowns. So if these solutions form a fundamental set, this happens if and only if y1 through yn are linearly independent. Again, same theory we've had before. Once again, we're going to have a Wronskian. So we are going to define the Wronskian similarly to how we did before. So note that y1 through yn linearly independent. Essentially can be written with matrix form. This is equivalent to, if we take each column to be one of our solution vectors, so let's put y1 in the first column, and then we'll do y1 in the last column of a matrix. Multiply this by the vector c1 through cn. So doing this multiplication, this would be precisely c1 y1 plus all the way through cn yn. So this is equivalent to our matrix y1 through yn multiplying the vector c1 through cn equaling that 0 vector has only the trivial solution. Well, that is equivalent to our matrix being invertible. So this is equivalent to our matrix where we put each vector y1 through yn as the columns. So this being invertible. And that is equivalent to the determinant being non-zero. So the determinant of the matrix where our y1 through yn are the columns cannot be zero. And so again, we call this determinant the Wronskian. I glossed through a few things here. Technically, each of these, since we are working with functions, not individual specific values, there's a little more to this than that. But again, we could look at the initial conditions. We know each IVP has a unique solution and take that route as well. But as I said, this is equivalent to the Wronskian being non-zero. So this is very similar to what we've already seen. And then we get a same theorem that we've seen before. So we have a theorem, which is that let's suppose that A of t, the matrix A of t, matrix function A of t is continuous on open interval AB. And consider the system, the n by n system, y prime is equal to A of t times y. Then the following are equivalent. First up, y1 through yn form a fundamental set of solutions. Next up, y1 through yn are linearly independent. Next statement, C1 y1 plus all the way up through Cn yn is the general solution. Next up, the Wronskian of y1 through yn is non-zero on AB. And last up, the Wronskian y1 through yn is non-zero at for some value of t in AB. Again, this is basically identical to the theory we've had before, just for differential equations. We're now generalizing it to systems. I realized as I was writing, I should have written one more thing, I believe, in my definition of a fundamental set of solutions. I should have said that we were dealing with solutions y1 through yn. So y1 through yn are solutions, then they form a fundamental set of solutions if they essentially span the solution set. Or if every solution can be written as C1 Y1 plus all the way through plus Cn Yn. All right, so that's the theory or basic theory for homogeneous linear systems.